In this lecture, we will look at some more examples of Jordan measurable sets. We have already developed quite a bit of theory for Jordan measurable sets, and in the last class we saw two examples which gave a wide class of Jordan measurable sets. So let's recall that the first one was about compact convex polytopes, and the second one was graphs of continuous real valued functions from a closed box B to R, where B is a subset of RD. So this is a closed box in RD. So as a corollary for the second one, we can establish some more examples of Jordan measurable sets. So as a corollary, we can state that finite unions of open or closed Euclidean balls are Jordan measurable. So an open Euclidean ball is of the form BXR. We will denote by BXR an open Euclidean ball. So the center will be this X, this is the center of the Euclidean ball, and R will be the radius of the Euclidean ball. So here X belongs to RD and R is a positive real number, and so this BXR is the set Y belonging to RD such that the Euclidean distance between X and Y is strictly less than R. So this gives you the open Euclidean ball of radius R with center X. Similarly, a closed Euclidean ball which is simply the closure of such open Euclidean balls BXR, and they are of the form, so the closure is simply the set of points in RD such that the Euclidean distance between X and Y is less than or equal to R. So one can check that in fact when you put less than equal to in place of strictly less than sign, then this set becomes the closure of the open Euclidean ball. So how do we prove this, that these are Jordan measurable? So note that it suffices to prove that one open or closed Euclidean ball of arbitrary center and radius, arbitrary center, let's say X, and radius R, is Jordan measurable, because we know that finite union of Jordan measurable sets is Jordan measurable. So if you have finite union of such open or closed Euclidean balls and each one is Jordan measurable, so the finite union will be Jordan measurable. So to prove this, we can simply apply the second part of the recall I mentioned before, this says that graphs of continuous functions are Jordan measurable. So we have to find a function f from R d minus 1 to R such that the closed Euclidean ball is the region under the graph of f, and this is given by this kind of sets that I denoted E plus before. This is simply the set of points xt in Rd such that 0 less than or equal to t less than or equal to fx. So we have to find such a function, and we can easily find one by just taking the equation of a sphere, a d sphere in Rd. So for example, if you have the 2 sphere in R3, so here we have R3, and you have the 2 sphere here we have the 2 sphere. We can separate these this sphere into the upper hemisphere. So this is the upper hemisphere, so for which this z coordinate is greater than or equal to 0, and this is the lower hemisphere for which the z coordinate is less than or equal to 0. So in this way we can write the closed Euclidean ball as a union of two things, and the region under which under each of these spheres or hemispheres becomes half of the Euclidean ball. So in this way we can take the union of these two halves to produce our closed Euclidean ball. So our function should simply be given by x1, x2, xd minus 1. So because it's from Rd minus 1 to R, and this is simply the square root, the positive square root of the function R square minus x1 square plus x2 square plus xd minus 1 square. So for example, here fx1 x2 should simply be R square minus x1 square plus x2 square. So that if you term this as z or x3, then x1 square plus x2 square plus z square is R square, and this is the equation of a sphere in 3 dimensions, a 2 sphere in 3 dimensions. So here we can take this function f to be simply given by the equation of this upper hemisphere, and then the region under the graph of f, which is, let me write this as the upper hemisphere with center 0 and radius r. This is given by xt belonging to Rd such that 0 less than or equal to t less than or equal to f of x. This is the upper hemisphere. And this corresponds to the fact that you have xd greater than or equal to 0 for this part. Here, as we had z greater than or equal to 0 in the z direction, here we can take the last coordinate xd to be greater than or equal to 0. And because this is the region under the graph, so u0r is is Jordan measurable. Similarly, the lower hemisphere is given by the graph of the function minus f. By the way, here we have to restrict our x1, x2, xd minus 1 to a closed box, and here the box is, so the f is defined, so let me write it here. F is defined on the Cartesian product of 0 r, so there are d minus 1 coordinates, and it takes values in r. Okay, so here rather than f, if we take minus f, we will get the lower hemisphere, which I also denote as L0r, and this is also is Jordan measurable. So the union of L0r and U0r, L0r, is simply the closed Euclidean ball with center 0 and radius r, and this is Jordan measurable. And the general case for when you want to replace the center, you can have arbitrary center x rather than 0, can be simply achieved by translation invariance of Jordan measurable sets. So this implies that Bxr is Jordan measurable for any x in Rd by translation invariance. By translation invariance, I mean that when you translate by x, then the Jordan measurability is invariant. So in that sense, it is translation invariant. It is also translation invariant in terms of the Jordan measure. So the Jordan measure of B0R closure and Bxr closure is also the same. So in this way, we can see that finite unions of open and closed Euclidean balls are Jordan measurable. The next set of examples comes from linear transformations. So once we know that a set is Jordan measurable, if we apply a linear transformation on that set and look at the image, we can ask the question whether the image set is Jordan measurable or not. So this is about Jordan measurability of images of Jordan measurable sets, under linear transformations. So by a linear transformation, I mean a matrix T from Rn to Rn. So it's given by an n cross n matrix, and this includes the cases. Of 1 rotation and 2 reflection, and both are given by the set of orthogonal matrices O. So orthogonal matrix, let's recall that and matrix is orthogonal if O transpose is O transpose O, and this is the identity on Rn, identity matrix on Rn. So we will look at rotations of Jordan measurable sets and reflections on Jordan measurable sets, and if you recall that our original goal to define the Jordan measure was to have an invariance of the measure under rotations and reflections and translations. So we have already seen that the Jordan measure is translation invariant, and next we will see that under rotations and reflections, and in particular for any orthogonal matrix, the first of all that the image is Jordan measurable, and second of all that the measure remains the same when you consider the image of a Jordan measurable set under rotations and reflections. So I am going to state it as a theorem. So let's look at the first part of the theorem. So I am considering L from Rd to Rd, a linear transformation. Then the first part says that if E is an elementary subset of Rd, then the image Le is also Jordan measurable, and there exists a constant C, a positive constant C, such that the measure of the image is C times the measure of E. The second part says that if E is now a Jordan measurable set of a subset of Rd, no longer an elementary subset, even then the image L of E is Jordan measurable, and this same equation as in the case of elementary sets continues to hold, which is that the Jordan measure of Le is C times M of E. This C is the same C as in part 1. And the third part of the theorem says that the constant C can be explicitly determined, and it is simply the modulus of the determinant of the linear transformation L. In fact, we can allow C to be equal to 0 as well. So this constant, which is given by the modulus of the determinant of this linear transformation L, can in fact take the value 0. Now the proof is a bit long, and we would require several steps, and we also need some facts from linear algebra. So for the first one, which is about the images of elementary sets, it's helpful to divide the problem in two cases. The first one is if first one from this case is when L is invertible, and the second one is when L is not invertible. So remember that this is equivalent to saying that if you want it to be invertible, then determinant of L must not be 0, and similarly if it is not invertible, then the determinant of L is 0. So in fact, for the first one, if we see, the third one should imply that our C should be 0 and the measure of the image should be 0, and this is what we expect, and this is for the second case when L is not invertible, because the determinant will be 0. So let's treat this case first. So if L is not invertible, then what happens? So in this case, we recall the rank nullity theorem, which says that the dimension of the image of L plus the dimension of the kernel of L is the dimension of Rd, which is simply D. So if L is not invertible, then the kernel has dimension strictly greater than 0. So for example, if so the dimension of the image is called the rank of L. This is equal to the rank of L by definition. So if the rank of L is equal to D minus 1, then the dimension of the kernel of L, then dimension of the kernel of L is 1, and one can also deduce that the dimension, this implies that the dimension of the kernel of L transpose is also equal to 1. So in this case, the image of L is simply the perpendicular of the kernel of L transpose, which is the set X in Rd such that X dot V naught equal to 0, where V naught belongs to kernel of L transpose, and because kernel of L transpose is one dimensional, this is the kernel of L transpose is simply the scalar multiplications of V naught. So says that lambda is in R. So because we have rank of L is d minus 1, then the dimension of kernel is 1, and so the dimension of the kernel of the transpose is also 1, and so it is generated, we can take as basis some vector V naught in kernel of L transpose, and any element of kernel of L transpose will be given by lambda times V naught. And so the image is the perpendicular of the kernel of L transpose, and this is simply given by the set of points in Rd such that X, the inner product of X and V naught is 0. So note that this is a hyperplane. Now this is a hyperplane equation in Rd, and we already know that hyperplanes have measure 0. First of all, they are Jordan measurable, and they have measure 0 once you have a bounded segment of the hyperplane. So if E is a box, then LE is contained in LRD, which is the image of L, and this is given by the hyperplane X in Rd such that X dot V naught equal to 0, where V naught belongs to the kernel of L transpose. So LE is contained in a hyperplane, and this implies that the outer measure of LE is less than or equal to the outer measure of some bounded segment of the hyperplane X dot V naught equal to 0, and this is 0. Here I am using the monotonicity for the Jordan outer measure. So this is using the monotonicity of Jordan outer measure, which is immediate from the definition of the Jordan outer measure. So we see that the Jordan outer measure for the image of a box, E is a box here, under the linear transformation L, has Jordan outer measure 0, which implies that LE is Jordan measurable with Jordan measure 0, with M of LE equal to 0, and this can be written as 0 times M of E, and this will be our determinant of L, because L has a rank strictly less than D, so the determinant is going to be 0. I'm sorry, the determinant of L is going to be 0, and so in this case C is determinant of the modulus of the determinant of L, which is 0. So we see that this equation is satisfied, and now we can, if we have an elementary set E, if E is an elementary set, then E can be written as a union of boxes BI which are disjoint from each other, and then M of E is given by the sum of m of bi I equal to 1 to n, and similarly the measure of LE then is going to be less than is equal to the measure of L union bi I equal to 1 to n, which by finite subadditivity will give you the sum of m LBI I equal to 1 to n, but each of these is 0, so this is 0. Therefore, again this can be written as 0 times m of E. So this is again satisfied when E is an elementary set and L has rank strictly less than D. In this case we have taken rank D minus 1, here we have taken D minus 1, but if it has even lesser rank than D minus 1, then it could be included in a subspace of rank of dimension D minus 1, and still it will be a subset of a set which has Jordan measure 0, so it will have Jordan measure 0. So here if rank of L is less than D minus 1, then image of L can be included in a set, in a subspace, let me call it V, where V is a subspace of dimension D minus 1, and this implies that the outer measure of image of L is well, L of E is less than or equal to the outer measure of a bounded segment of V, which is going to be 0, because V is a subspace of dimension D minus 1. So again we see that if you take any rank less than D minus 1, then again the outer measure is going to be 0, and we can repeat the same argument to prove that LE is Jordan measurable. So we have proved that if E is an elementary set and L has a rank less than D, strictly less than D, then LE is Jordan measurable with Jordan measure 0. So now we come to the case when L is non-invertible, which means that the determinant of L is not equal to 0. Here I am going to use the fact that if M prime is a map from the elementary subsets of RD to 0 infinity, which satisfies monotonicity, translation invariance, and finite subadditivity, then M prime of E is some constant alpha times M of E, where E is Jordan measurable for where E is elementary for any E in the elementary subsets of RD. So this was the uniqueness theorem up to scalar multiplication for the Jordan measure. Any other measure which satisfies monotonicity, translation invariance, and finite subadditivity must be a constant multiple of the Jordan measure, of the elementary measure. So if we define M prime from the elementary subsets to 0 infinity as M prime of E is M of LE, then one can show that this satisfies monotonicity, translation invariance, and finite subadditivity. Then check that M prime satisfies monotonicity, translation invariance, and finite subadditivity.